In this video, we're going to talk about 2.5 Objective 3, where we find horizontal and vertical asymptotes of functions. Let's go ahead and get started here. As I go to the right here, I'm going to approach 2 over 6. I'm just going to use my pre-calculus rules here to say that I get close to 1/3. As I get a big positive number, same thing as I get a big negative number, I'm going to get close to -2 over -6, which is going to be a positive 1/3. And my function has a horizontal asymptote at y equals 1/3, and it has vertical asymptote that they didn't ask us about, but the vertical asymptote is going to be at -5/6. So VA x equals -5 over 6 is going to make the denominator 0. Okay, degree of the top and degree of the bottom are the same. So 4 over 2 is 2. Just using pre-calculus rules, I'll get to where I need to use calculus in a little bit. You can use all the techniques that I just used in the last video to find limits at infinity with multiplying top and bottom by the reciprocal of this biggest degree here. And that's going to be what gives you your rules from pre-calculus. 15 over 3 is going to be 5. And you have one asymptote at y equals 5. Okay, this one, degree of the top is smaller than degree of the bottom, so we're going to be getting closer to 0. Top and bottom. One horizontal asymptote at y equals 0. Degree of the top is smaller than degree of the bottom, so again, y equals 0. Degree of the top is bigger than degree of the bottom now, so now we need to be careful what the asymptote is, and we're going to have to maybe use some long division to help us here, but I'm just going to simplify this into 39x plus 3x to the -4th over 18 minus 4x to the -5th. So as I go to positive infinity, this goes to 0, this goes to 0, and I get and this goes to positive infinity, that's going to go to positive infinity. As I go towards negative infinity, this goes towards negative infinity, that's 0, and that's a number. Going to get close to negative infinity. And the function has no horizontal asymptote, it has an oblique asymptote or a slant asymptote, whatever your teacher calls that. Okay, we've got these square root ones. Remember that these might give us 2 different horizontal asymptotes. We need to check here. So this comes out as the absolute value of x. Square root of 64 plus 5 over x squared over 9x plus 5. Still degree 1, top and bottom, but this is positive when I go to the right, negative when I go to the left. So this is going to be 8x over 9x. This approaches as x goes to positive infinity. And this is -8x over 9x is what it approaches as x goes to negative infinity. So this is 8 over 9 on the positive side, and this should be a negative 8/9 on the negative side. And it has two horizontal asymptotes. The top one is y equals 8/9, and the bottom one is y equals negative 8/9. Okay. um, let's look here. If I make this equal to 4x to the third plus 2, for x to the third plus the absolute value of x to the third, square root of 4 plus 2 over x to the sixth. This is always a positive number. But this is, let's see here, the same as 4x cubed plus 2 for x cubed plus x cubed square root 4 plus 2 over x to the sixth when x is greater than 0, and 4x cubed plus 2 for x cubed minus x cubed square root of 4 plus 2 over x to the sixth when x is less than 0. So when I divide everything by x to the third here, in the top, I would get a limit of 4 plus 0 over 1 plus root 4 plus 0. And 4 over 1 plus 2 is 4/3. And then in the bottom piece here, I'm going to get a limit of 4 plus 0 over 1 minus square root of 4 plus 0. So that's going to be 4 over 1 minus 2 is 4 over negative 1 is a negative 4. So I have two asymptotes, with the top one being y equals 4/3 and the bottom one being y equals negative 4. About halfway through, let's go ahead and look at this one as, pull this out. This is an odd exponent, so this is just plain old x squared. X 1 plus 64 over x to the sixth over 2x squared. This is an even index, so when I pull the squared out, it's going to be like that. I don't need absolute value bars around that because it's already going to be positive because it's an even power. So this is going to simplify in all cases to this. And then when I take the limit as x goes to infinity, that's going to be cube root of 1 over 2 plus square root of 7. And it's going to be the same on both sides. That's 1 over 2 plus square root of 7. Top and bottom, like that. So there's one horizontal asymptote at y equals 1 over 2 plus square root of 7. I'm not worried about rationalizing that. Right? Let's determine whether the following statements are true. You give an explanation or counterexample. The graph of a function can never cross one of its horizontal asymptotes. That's false. We can cross the horizontal asymptotes in the middle of the graph. It's just the horizontal asymptotes talk about the end behavior of what happens at infinity and negative infinity. It doesn't have to do anything with small values that are in the middle of the graph. So that's false. For example, the graph of f of x equals 3 plus 10 sine x over x crosses the horizontal asymptote of y equals 3 multiple times. For question B, a rational function f can have both limit of f of x as x approaches infinity equals L, where L is finite, and limit as x approaches negative infinity of f of x equals infinity. That is false for a rational function. The limit as I of the function as I approach negative infinity and the limit as I approach the function of positive infinity are either both finite or both infinite. So that's A. You can't have one side go to infinity and the other side go to a finite number. Let's choose the correct answer for C. The graph of any function can have any number of vertical asymptotes, but must have at most 2 horizontal asymptotes. That is true. So the denominator of a rational function can have any number of zeros, each of which creates a vertical asymptote if it doesn't cancel out with something in the numerator as well and give me a whole. If the limit at that zero goes to positive or negative infinity, that's what they're saying. It doesn't create a hole there. However, horizontal asymptotes are about end behavior on the left as x, so the limit of the function as x approaches negative infinity, and the right, the limit of f of x as x approaches infinity. So there are only 2 directions. So there can be at most 2 horizontal asymptotes. D asks us to evaluate this limit here, see if this is correct, that as x approaches infinity of x cubed minus x, that you could split that up into x limit of x cubed as x goes to infinity minus the limit of x as x goes to infinity is infinity minus infinity. And can you subtract infinity from infinity and get 0? You cannot do that because you do not know that those infinities are the same sizes. In fact, we know for sure that if we had this graph of x cubed that had a positive coefficient, even though it has an x there, it's times x squared minus 1, which is x times x plus 1 times x minus 1. And we go through 0, 1, and negative 1. We know that this over here is positive and increasing, and this is negative and decreasing here, and it goes up and then comes down through here, then goes back up. But we're interested in this end behavior as it goes to positive infinity is going to be positive infinity, not 0. We cannot do infinity minus infinity to get 0. That's called an indeterminate form. The only way we know that those infinities subtract out is if they're the same size, and that's complicated right now. We don't really want to talk about different types of infinity right now. But x cubed is growing much faster than x. It's more powerful as we go out to the end, so we kind of ignore the x part and only care about the x cubed part is what's going on here. So the answer for D is that this is false, even though the limit laws are applied correctly. The result of infinity minus infinity has an indeterminate value. We'll talk much more about indeterminate values later. It is not true that infinity minus infinity must be 0. To avoid this problem, use the leading term to determine the limit which is equivalent to factoring out x cubed and then taking the limit. So B, so they're telling us that if we had done limit as x goes to infinity of x cubed minus x, and this was the same as limit as x goes to infinity of x cubed times 1 minus 1 over x squared. And then this limit would have been infinity times 1 minus 0 is infinity times 1. It's infinity. And again, you're not supposed to treat infinity as a number here, but that's the idea, is that this isn't doing anything other than maybe changing the sign here. That's why you have to take that into account, as if this piece goes to a -1, that's going to make that a negative infinity. All right, let's do a little bit more here. Consider the function f of x equals 2x cubed plus 16x squared plus 30x over x to the third plus 5x squared. We're going to rewrite that as 2x plus, as 2 plus 16x to the negative first plus 30x to the negative second over 1 plus 5x to the negative first. We want to see what happens as x goes to infinity. We're going to get close to 2 over 1 is 2. And as we get close to negative infinity, it's also going to get close to 2 over 1 is 2. The denominator here is x squared times x plus 5. There's one horizontal asymptote at y equals 2. Vertical asymptotes, so denominator. And let's just look at that numerator. X times 2x squared plus 16x plus 30. Take that 2 out. It's 2x times x plus 3 times x plus 5. So we have 2x times x plus 3 to x plus 5 over x squared times x plus 5. The x plus 5s will cancel. The x will cancel. I'm left with 2 times x plus 3 over x. X cannot be equal to -5. So there's only one vertical asymptote at x equals 0. And as I get close, looking for the option that says, yeah, this one, B, x equals 0. And as I get close from the left, I go to negative infinity. As I get close from the right, I go to positive infinity. All right. So more questions here. This is going to be 3 plus 6x to the negative first minus 72x to the negative second over 1 minus 52x to the negative second plus 576x to the negative fourth. So our horizontal asymptotes left and right are both going to be 3. And there's going to be one horizontal asymptote at y equals 3. Let's look at factors of numerator and denominator here. 3x squared times x squared plus 2x minus 24 over, and this is going to be x squared minus an x squared minus 576. Breaks down into 2 times 2 88, which is 2 times 144. All right, so that is 4 times 144. It's a good starting point. See if I've got 8 and 72. Nope, still not close enough. 16 and 36. Yeah, that's it. 16 and 36 here. This is going to break down into 3x squared times x plus 6, x minus 4. This will be x plus 4, x minus 4, x plus 6, x minus 6, x plus 6, and x minus 4. Cancel off, and I'm left with 3x squared over x plus 4, x minus 6. X cannot be equal to -6 or 4. So I have vertical asymptotes, 2 vertical asymptotes at x equals -4 and x equals +6. It's number 12. Leftmost is at x equals -4. The rightmost is at x equals 6. Leftmost asymptote is going to, let's just look at what happens here. -4 and 6 are my asymptotes. I also have a hole at -6, and I have a hole at +4. And if I look at the factors here, that this is going to be something to the left of -6 is going to be, let's just look at something here like -5. That's all I care about, because I care about this behavior from the left of that. That's positive over negative times negative. That's going to be positive going to positive infinity. Let's look at something like -3. That's positive, positive, negative. So that's going to be negative on that side. Something like 5 is going to be positive, positive, negative. That's going to be negative on that side. And something like 7 is going to be positive, positive, positive. So this is going to be for -4 from the left, we're going to go to infinity. And from the right, we're going to go to -infinity. And then for the rightmost, from the left, we're going to go to -infinity. And the right, we're going to go to infinity. All right. This is the same as x plus 11, x minus 11 over x times x minus 11. That cancels and leaves me with x plus 11 over x, as long as x is not 11. And our horizontal asymptote here is going to be equal to 1, both from the left and the right. And the function is only going to have one horizontal asymptote at y equals 1. And vertical asymptotes, we're going to have x equals 0 is going to be our only vertical asymptote. So that's B. And so I go to the left of 0. This is positive over negative is negative infinity. To the right, it's going to be positive infinity. All right, This is x squared minus 20 over x squared plus 20 over x squared minus 20 squared plus 20. X can't be equal to plus or minus root 20. And this is going to have no horizontal asymptote. This is going to go to positive infinity. This is also going to go to positive infinity on both sides, since it's got an even power like that. The limit exists in this positive infinity, but it doesn't have any horizontal asymptote. How many vertical asymptotes? It's going to have none. It's going to have some poles, but the function has no vertical asymptotes. Moving on to number 15 here. We're going to it's going to give me, as I go to the right, it's going to give me 3 minus 0 over 1 minus 0. Three over 1 is 3. And then from the left, that's going to give me a negative 3 minus 0 over 1 minus 0 is a negative 3. And it has 2 horizontal asymptotes. The top one is y equals 3, and the bottom one is y equals negative 3. And so we don't have a vertical asymptote here. If I actually try and stick 1 in here, I get 0 over 0, which means that there's something that would cancel. I'd have to actually rationalize the numerator to figure out what's going on, but there's a hole in the graph there. So let me just show you what that would be. 9x squared plus 2x plus 14 minus 5 times 5 is 25 over x minus 1 times root 9x squared plus 2x plus 14 plus 5. And then if I take the limit of this as x goes to 1, let's take limit as x goes to 1, 9x squared plus 2x minus 21 over x minus 1. This is 14, so that's 11. There we go. Times that square root thing plus 5 is going to give me 9 plus 2 is 11. That's 11 is 0. Over 0, still do some factoring here. X minus 1. This is going to be 9x plus 11 here over x minus 1 times that square root thing plus 5. And you're going to see that I get a finite limit there. It's going to be like 20 over 2, 4, 18 plus 5 something crazy. It's still got a square root in the denominator, but it's not going to be a vertical asymptote. So there's no vertical asymptotes. The vertical asymptotes are going to have to approach positive and negative infinity. Let's consider the function 36 minus x squared inside of absolute value bars is 6 plus x, 6 minus x over x times x plus 6. It's the same thing as x plus 6 times x minus 6 over x times x plus 6. And so as I go to positive infinity, these are all positive numbers, and this will cancel, and I'll have what looks like x minus 6 over x is going to be 1 minus 6 over x. That's going to go towards 1. And as I go towards negative infinity, we're going to have a negative times a negative down here, but the numerator is going to be positive, so that's still going to be positive. 1 here, as this will be the opposite of this, and this will be the opposite of this, and those will cancel each other out over and I'll still be left with that function. As I go to negative infinity, that's still going to go to 1. So nothing really changed because degree of the top and degree of the bottom are both even there. The function has one horizontal asymptote at y equals 1. And it has, it doesn't have a vertical asymptote at x equals negative 6 because in both cases, that's going to cancel and make a whole. It does have a vertical asymptote at x equals 0. So D and from the left here, that's going to be from the left, it's going to be negative and a negative. So that's going to be a positive. And from the right, it's going to be a negative and a positive. So that's going to be a negative. I said that backwards. This negative over negative is positive. Yeah. Oh, this is a negative up here because of the absolute value sign. When I come from the left, yes. I need to look at that on the graph. So let's go ahead and open up Desmos. Look at equals absolute value 36 minus x squared divided by x times x plus 6. All right, and we have horizontal asymptote here that we're getting close to 1 here, both on the right and the left-hand side. Vertical asymptote here at x equals 0, it goes to negative infinity on the left, positive infinity on the right. So negative infinity on the left, and positive infinity on the right. Sometimes the best thing to do with these is just to look at them in a graphing calculator, and that's why some of these will even say that they're technology questions. And do that here. Square root of the absolute value of x minus square root of the absolute value of x plus 1. Square root of the absolute value of x minus square root of the absolute value of x minus 1. Like that. We're going to zoom in so you can see what's going on here. I'm getting close to 0 from both the top and the bottom. I have these cusps here, but I don't have any holes. What I'm going to want to do probably is write this as two separate functions here as square root of x minus square root of x minus 1 as I'm going towards positive infinity, and then rationalize this as x minus 1 over square root of x plus square root of x minus 1 is going to give me 1 over, and then that's going to go to infinity. It's going to go to 0 on the right-hand side. And then on the left-hand side, this is going to be square root of negative x minus square root of negative x plus 1. Just take the opposite of what's inside because these things are becoming negative values and I can't have a negative inside, over 1. And then I'm going to multiply by the conjugate. So this is going to be a negative x minus that is going to be plus x minus 1 over root negative x plus root negative x plus 1. And this is going to be big negative number, big negative number. These are going to infinity. So this is going to infinity down here. This is a negative 1 up top. That's going to go to 0 as well. And the function has one horizontal asymptote at y equals 0. And if we have already looked at the graph, it has no vertical asymptotes. So, and we would have guessed that because there was no denominator here, but there's also nothing that can make this denominator 0 down here when we rationalize it. All right, this is 3x over absolute value of x, square root of 1 plus 5 over x, plus 4 over x squared. So this is 3 over 1 is 3. As I go to positive infinity, and this is negative 3 as x goes to negative infinity. There's 2. Y equals negative 3, and y equals 3. Vertical asymptotes here. Square root of x plus 1, square root of x plus 4. And so -1 and -4 are going to give me zeros in the denominator. So there are two vertical asymptotes, -4 and -1, like that. Okay. Consider the function here. Like that. And this is going to stay between -1 and 1. This is going to go to infinity, so this part's going to go to 0 as I take the limit as x goes to infinity, and we're going to get close to 11 both times here. And as I go to negative infinity, that's not going to work. I can't take the square root of negative infinity, so that actually doesn't work. There's no horizontal asymptote on the left-hand side, only on the right-hand side, because x needs to be greater than or equal to 0 for the domain. I'm sorry, greater than 0 strictly for the domain. Can't have it equal 0 because it's in the denominator. Can't have it less than 0 because it's in a square root sign. So there's going to be no activity on the left-hand side to have a horizontal asymptote on the left. So there's one horizontal asymptote, and there is one vertical asymptote. Let's see what it has to find the vertical asymptote, and it's at x equals 0. And it's only going to have behavior from one side. So B x equals 0. So from the left, it doesn't exist, and from the right, it's going to go to this is going to be a negative infinity. This is getting close to -1 as x gets close to 0, and this is getting close to infinity here. So -1 over infinity, that's going to be a negative infinity. All right, that's it. We'll come back next time and we'll talk about 2.5 objective 4. See you for the next video.